first, we need to know about the naming. Unlike the alkenes, if we have the alkane here, if we take out one of the hydrogen, this is CnH2n plus 2, take out one hydrogen, they become alkyl, which is CnH2n plus 1. So if we have methane, they become methyl. If we have, example, methane become methyl. If we have ethane, become ethyl. If we have propan, become propyl. With a similar idea here, we're going to have the class of aromatic hydrocarbon. We call them arene, okay, and that's become aryl. But it's not about Peter Pan. So the simplest of the arene is the benzene. Okay, and we're going to call them should be benzyl. That's in theory. But in practice, very seldom we're going to call them into benzyl. In fact, we're going to call them into phenyl. Why? Because another name of benzene is phenyl, but very seldom we're going to use those names. So there are times you're going to have benzyl, but most of the time here, you're going to call them into phenyl. That is benzene that lost one hydrogen. Okay. So if you take one hydrogen, the name change from benzene into phenyl. That is the first part of the naming. Okay. So if we have alkene, we have them alkene. The major part, we call them arene. Then the other part, we're going to call them aryl. The second is about the numbering and position. We will need to memorize the name of the substituted benzene. The most important one here, if this is hydrogen, we call them benzene. If this is going to be hydroxide, we're going to call them phenol. It's from phenol. If this is chloride, we call them chlorobenzene. There are some of them here that you already have them here, and I'm not going to put all of them, but I do put them here that those in page 383 must be remembered. So I'm going to put them here. If this is amine, we're going to call them phenylamine. In most books, you're going to call them aniline. And if we have them here, and O2, we call them nitrobenzene. If this is COH, this is aldehyde, we call them benzaldehyde. And if you have them here, COOH, acid with oxygen here, it's going to be benzoic acid. Well, the truth is, the name is benzoic acid first. When we know that the benzoic acid has this structure, the original structure, then we call them benzene. But it is because this acid, we call them benzoic acid, Hence, the major structure here we call them benzene, not the other way around. So the name benzoic acid comes first. When people know the structure, so the structures within benzoic acid, we call them benzene. Okay, now this is the basic idea. One thing, almost forgot. If this is CH3, we call them toluene. Now those are the 8 basic substitute benzene that we have to memorize. Okay. They are representing the basic functional groups of chemistry. Hydroxyl, hydrogen, hydroxyl, chlorine, alkyl, amine, nitro, carbonyl, and carboxyl. Hydrogen, hydroxyl, we call them halogen, okay, halide, okay, and alkyl. Chlorobenzene is the name here. Of course, you can also see in some publications phenyl chloride. But the name phenyl chloride is in IUPAC being discouraged because the ending chloride is usually used for salts, and it's not salt. Phenyl chloride is actually covalent substances. Okay, now assuming all of you already take note of this, I'm going to erase. Anybody still take note? No, good. Second part we're going to take out today is about the structure. The benzene is unusual because they have 1.5 part here. Why do you have a dot here? The dot here is to emphasize that all the bond here is identical. In the past, we're going to see benzene with a Kekulé structure. This will come Kekulé structure from the German who give the first possible arrangement of benzene. So in Kekulé structure here, benzene is thought to be having 3 double bonds and 3 single bonds. After careful calculations, we know that this is not true because the length of the double bond is shorter than the length of single bond. We know that. But the benzene's length of bond is halfway between single and double bond. It is shorter than single bond, but longer than double bond. So think of them like 1.5 bond. If we know that carbon must have 4 arms, Kekulé is the simplest who give us 4 arms per carbon. 1, 2, 3, 4. 1, 2, 3, 4. But this implies the double bond and single bond with different length and different strength. Our measurement of benzene find out that all bonds are of same length, identical. Hence, we are going to use the donut inside this to emphasize that this is a circular arrangement. Think of this like having 1.5 bonds all over. So 1.5 live, 1.5 here, the fourth one there. 2 times 1.5 is 3, right? So 3 bonds with carbon, each 1.5, and the last one here. How can this happen? This happens because we have a pi bond that was being delocalized. If we recall into the AS level, there are 2 types of bond between atoms. There are actually three, but you haven't got the three. First, we call the sigma bond. Sigma bond happen if we have orbitals that merge in between two nuclei. This is the first atom. This is the second atom. If the first atom here, individually as an atom, has orbital, like this one, for example, atomic orbital, and B, also this type of orbital, one of them bigger and the other smaller, and they join together, the orbital is going to look like this. The overlapping of these two orbitals gets big area in between the two nuclei. A and B are the nuclei of the atoms, and this one is the orbital in between them. Remember what orbital is? Orbital is space where we are likely to find the electron. Now, in this case here, the electrons are likely to be in between them. Sometimes they go into the other side of the atoms, but they're going to mostly spend their time here. We usually put them as a straight line B. This is how we usually write simplification of their covalent bonding. But it is important to understand that electron is not static. It's not like a bar not going anywhere that is going to hold two ends of balls. Instead, they are more like forces of nature that is going to hold the two positive nuclei together. They are being negative. This type of bond, we call them sigma bond. Sigma bond has their orbital in between two nuclei. Now, we're going to have a second type of orbital that we call pi orbital. Pi bond happen if we have pi orbital. This is going to be the S orbital, and the result becomes sigma bond. S orbital happens between the two nuclei. Now, if we have nuclei A and nuclei B, each of them has orbital perpendicular to them, here and there. If they are joined together, let's say A and B is joined together, close enough, then the orbital of A and B is going to merge them. I'm not very good at sketching, but just think of them as being close together and merge. Now, this type of bonding, we call them pi bond, comes from the p orbital. The pi orbital is going to make up the pi bond. A pi bond is located parallel to the line connecting the two nuclei, but not within them, not between them. They are parallel, but not within them. If it's within them, that's going to be a sigma bond. Between any two atoms, there has to be always sigma bond between them. Parallel to the sigma bond, it is possible to have pi bond. Remember that the pi bond always comes in couple. We cannot have just top pi bond or bottom pi bond. No, two of them. As a group, we call them a pi bond. So a pi bond consists of two parts, while a sigma bond is always one part, single part in between them. Now, the reason why the benzene has their unusual condition is it comes from the fusion of 6 pi orbitals together. And they're going to join together and produce a donut-like condition. Okay, you may